Hello and welcome to this lecture. In this lecture, we're going to look at Hermitian matrices and the associated spectral theorem. So, we've seen in the previous lecture symmetric matrices and the real spectral theorem. We're going to see Hermitian matrices and the associated spectral theorem here. Okay, so what's the basic idea? Again, we'll start with R2. Okay, without understanding, not R2 here, dimension 2, which is C2. Okay, so we'll start with C2. Without understanding C2, we have very little hope of understanding Cn. So, we will start with C2 here. So, I will look at an operator T from C2 to C2 and then look at say that maybe it is represented by a matrix A, B, C, D, and A, B, C, D are now complex. Okay. So, previously we had looked at the case when A, B, C, D were real. It was simple enough to understand, but now A, B, C, D could be complex with respect to some canonical basis. I am going to assume T is diagonalizable. So, it is represented by a lambda 1, lambda 2 diagonal matrix with respect to some eigenvector basis, and this V1, V2 are linearly independent. And here is my crucial assumption, I am going to assume lambda 1, lambda 2 are real. Okay. So, I want the eigenvalues to be real. Okay. So, you know it is a complex matrix. So, eigenvalues are real, eigenvectors are going to be complex. Right. So, that is going to happen. So, eigenvectors could be complex. So, this is the difference from the real case. When you had R2, everything was real. Now, I am going to go to C2, C2. I am going to allow the eigenvectors to be complex, but I am going to say lambda 1, lambda 2 have to be real. Okay. So, this will lead me to this Hermitian matrix and the associated spectral theorem. So, now the same question I am going to ask. Okay. So, before that, just a quick warning on how these things work. We have seen it before. The inner product between V1 and V1 is the norm of V1 squared, and that has this definition. Notice the conjugate comes in. It is the same as norm V11 squared plus norm V12 squared. This is not norm, it is absolute value, is magnitude of V11 squared. Remember, V11 is complex, right? So, magnitude of V11 square plus magnitude of V12 square. Likewise, norm V2 square is also norm magnitude of V21 square plus magnitude of V22 square. We will assume orthonormality here, and the inner product between V1, V2 is similarly defined. Okay. So, this is the conjugation. Be careful about the conjugation. Okay. So, just to tell you how that works. So, now I am going to ask the question, under this situation for a diagonalizable operator, if the eigenvectors end up being orthonormal, what happens? What can I say about A, and is there a converse, right? So, that is the question I am going to ask here. You can see for the dimension 2 case, this is easy enough to characterize. Okay, we have always start with the AS equals SD, right? I got the AS equals SD here, and now the inverse of this matrix is again easy to find out. What is the inverse of this matrix? It is the Hermitian of this matrix, right? So, you can see you have to conjugate and take transpose. Okay, so it becomes the Hermitian. Okay, so that is a very simple observation. Once you do that, we can repeat what we did before. Okay, so A becomes just this matrix S, columns are eigenvectors, times D times the conjugate transpose of the original matrix. Now, when you multiply this out and simplify, you get this kind of an expression. It looks a little ugly, but it has a structure to it. Okay, so it is much simpler than the general case. And what is the structure? The first thing you can look at is the diagonal values are real. Okay, so that is one point. Because lambda 1, lambda 2 are real, I assume lambda 1, lambda 2 are real, diagonal values are real, you have just magnitude square, and then the off diagonal values are conjugates of each other. Okay, if you stare at it closely, you have got lambda 1, lambda 2, and then if you take conjugate, you are going to get this guy. So, what happens, what do you notice here? So, the off diagonal values are conjugates and the diagonal values are real, which means this A is the same as its Hermitian. So, A equals A Hermitian. Okay. So, what we get here is some sort of an equivalent to what we had earlier. When the R2 to R2 case, we saw if T is orthonormally diagonalizable, then the matrix was symmetric, A equals A transpose. Notice what happens in C2 with real eigenvalues. The eigenvalues being real is crucial here, that is very important. So, if T is orthonormally diagonalizable with real eigenvalues in C2 to C2, then its matrix is defined to have this Hermitian property. What is the Hermitian property of a matrix? If A equals A Hermitian, it is called Hermitian. If A is A transpose, it is called symmetric. If A equals A Hermitian, it is called a Hermitian matrix. Okay. So, what about the converse? Is the converse true? Supposing we start with the Hermitian matrix, is it true that it has real eigenvalues? Is it true that it has orthonormal eigenvectors? Okay, that is the converse we are going to check. Okay. So, let us start with an operator T from C2 to C2, and maybe it is represented by a complex Hermitian matrix A. Hermitian meaning A comma D, A and D will be real, and then B will be equal to B bar, right? I mean not B equal to B bar, B is the off diagonal elements are conjugates of each other. So 1 comma 2 is B and 2 comma 1 is B bar. Okay, so once you have this, we see that A equals A Hermitian, it becomes a Hermitian matrix. Maybe this is with respect to a canonical basis, it can also be another orthonormal basis. Okay, so now how do you find eigenvalues for this? It's the same formula, right? But notice what happens here, you get A minus lambda, D minus lambda minus mod B squared. Okay, so this makes all the difference. So the eigenvalues actually become real. Okay, so if you note it down, you'll see that what's inside the square root is the sum of two squares. So that's non-negative. So you get real eigenvalues. So the eigenvalues are real. Okay, so that's pretty promising. If you have a Hermitian 2 by 2 matrix, its eigenvalues are real. Okay, so it's very easy to establish. Okay. What about eigenvectors? If you go through and write down the expression for eigenvectors, you will once again see that the eigenvectors are orthogonal to each other. Okay, so notice B can be complex here. Okay, B is complex. This value actually ends up being real, but then B is complex. So you have to be careful when you do the inner product. But if you do the inner product, you will get 0. Okay, so you can check this. I'm not checking this for you. This works out. So in summary, if T from C2 to C2 is represented by a complex Hermitian matrix, then it has real eigenvalues and is orthonormally diagonalizable. Okay, this is very, very similar to what we had earlier with symmetric matrices. Okay, now does this extend in general? Okay, but before that, let's see an example. Okay, so examples are important to see. Once again, it's very, very simple. This 1, 2i minus 2i, you can note 1, you can see that this is a Hermitian matrix. Go through, compute the eigenvalues. Of course, the eigenvalues are real. Eigenvectors end up being complex, but they are orthonormal. We know that these two and dot product will get 0. Again, you can write the same A equals SD S inverse, which is actually S Hermitian, right? If you write that, you get this nice spectral decomposition type property, lambda 1 V1 V1 Hermitian plus lambda 2 V2 V2 Hermitian, and this is a general form of any 2 by 2 Hermitian matrix. You can put real eigenvalues lambda 1 lambda 2, take your own favorite orthonormal basis and write V1 V1 Hermitian, V2 V2 Hermitian, add it up, you will get a Hermitian matrix. That's all the Hermitian matrices that are out there. You can go through and multiply. I'm just trying to repeat it to show you how this works. And powers are also very, very easy. Because of the orthonormal property, powers become simply powers of lambda, and that also you can check. Okay, so this kind of an orthonormal decomposition becomes possible for Hermitian 2 by 2 matrices. And guess what? The general case is also true, and that is the spectral theorem. A general operator T from Cn to Cn, if it has real eigenvalues and is orthonormally diagonalizable, then its matrix becomes Hermitian, of course with respect to some orthonormal basis. Hermitian, A equals A Hermitian, and the converse is also true. If you have for any n by n matrix, if it is Hermitian, if A equals A Hermitian, then its eigenvalues are real, and not only that, it is orthonormally diagonalizable. It has an orthonormal basis of eigenvectors. Okay, once again, the proof sketch for general n will come out later. Let's just look at how these matrices look. A Hermitian n cross n matrix looks like this. All the diagonal values are real, and the off diagonal values are conjugate symmetric about diagonal. Notice this A12 is A12 bar, A1n is A1n bar, A2n is A2n bar. Okay, so A equals A Hermitian means this kind of a structure. So again, very easy to verify. If you look at the matrix, if it ends up being Hermitian, then you know eigenvalues are real and the eigenvectors are orthonormal to each other. Okay, so that's very nice. Once again, real eigenvalues are there. You can order them. You can write lambda 1 greater than or equal to lambda n. Then you have orthonormal eigenvectors, and you can express them in this fashion. Okay, and then what is our general form? This spectral decomposition form for a n by n complex Hermitian matrix. I'm going to repeat the same thing. It's going to look exactly the same, except for transpose we now have Hermitian. Okay, so instead of in the real world you have transpose, in this complex real eigenvalue world you will have Hermitian. You write it down, you get a general form like this, and then the powers behave in the similar fashion. You just have to square the lambda, and then you get the powers, and A par k also behaves in the same fashion. All the proofs are exactly the same. You just have to not change anything. Okay, so this is another very, very powerful spectral theorem result. Even if you have a complex matrix, right? If that complex matrix is Hermitian symmetric, okay, if the real matrix is symmetric, then you got a nice orthonormal basis of eigenvectors, and you got this very nice form for the matrix A. Now for a Hermitian matrix, you again have a similar form, and it's complex, but then the eigenvalues are real, the eigenvectors may be complex. Okay, so this is the second spectral theorem we are seeing, the Hermitian matrix spectral theorem, and I hope this is interesting and clear to you. Thank you very much.